Lecture 9, Symmetric Cryptography. Theme: Cryptography, Symmetric and Asymmetric. Technical University of Moldova. Lecturer: Maxim Masayutin, Associate Professor. Introduction. Hello, everyone. Welcome to Lecture 9, where we dive deep into the fascinating world of symmetric cryptography. This is arguably one of the most fundamental topics in information security, and understanding it thoroughly will serve as the foundation for everything else we discuss in this course. Let me start with a simple question. What happens when you send a message over the internet? How does your bank ensure that nobody can read your account balance while it travels through dozens of routers and networks? The answer, in most cases, involves symmetric cryptography. Consider this. Right now, as we speak, billions of encrypted connections are active across the globe. Every HTTPS website, every secure messaging app, every VPN connection relies on symmetric cryptography for the bulk of its encryption. While we will study asymmetric cryptography next week, I want you to understand that symmetric cryptography does the heavy lifting in modern security systems. Today, we will cover the principles that make symmetric encryption work, explore both historical and modern algorithms, and understand how to use these tools correctly in real-world applications. By the end of this lecture, you will understand not just what these algorithms do, but why they work and how to choose the right one for your specific needs. Let me outline what we will cover today. First, we will examine the fundamental principles, the mathematical and conceptual foundations that all symmetric ciphers share. Then we will compare block ciphers and stream ciphers, understanding when to use each. We will take a historical tour through DES and triple DES to understand why they are no longer suitable. The bulk of our time will be spent on AES, the current standard, including its various modes of operation. We will also explore ChaCha20, the modern challenger to AES, and Ascon, the new lightweight cryptography standard. Finally, we will discuss key management, often the weakest link in cryptographic systems. Part 1. Principles of Symmetric Encryption. The basic concept. Symmetric cryptography, also called secret key cryptography, is the oldest and most intuitive form of encryption. The fundamental idea is remarkably simple. Both the sender and receiver share the same secret key. This key is used both to encrypt the plaintext into ciphertext and to decrypt the ciphertext back into plaintext. Think of it like a physical lockbox. You have a box with a lock, and you make two copies of the same key. You keep one, and you give the other to your friend. Now you can exchange secret messages by putting them in the box. Anyone who intercepts the box cannot read the message without the key. This analogy has been used for centuries, and the basic principle remains unchanged in modern cryptography. Mathematically, we express this as encryption. The ciphertext C equals the encryption function E applied to the key K and the plaintext P. Decryption. The plaintext P equals the decryption function D applied to the key K and the ciphertext C. The encryption function E takes two inputs, the key and the plaintext, and produces the ciphertext. The decryption function D reverses this process using the same key. This symmetry in key usage is what gives symmetric cryptography its name. The security of the entire system depends on keeping the key secret. If an attacker obtains the key, all security is lost. This is fundamentally different from asymmetric cryptography, which we will study next week, where different keys are used for encryption and decryption. Let me emphasize something critical here. The key is everything. You could use the most sophisticated encryption algorithm ever designed, but if your key is weak, predictable, or leaked, your security is worthless. We will return to this theme repeatedly throughout this lecture. Historical context, from Caesar to computer. Before we dive into modern algorithms, let me briefly mention the historical development of symmetric cryptography. The Caesar cipher, used by Julius Caesar himself, simply shifted each letter by a fixed amount. If your key was 3, A became D, B became E, and so on. This is a symmetric cipher. The same shift value encrypts and decrypts. The weakness of the Caesar cipher is obvious. There are only 26 possible keys. You can try them all in minutes by hand. This leads us to an important principle. The key space must be large enough that brute force searching is impractical. Over the centuries, ciphers became more sophisticated. The Vigenère cipher used a keyword to determine variable shifts. The Enigma machine used rotors and plug boards to create complex substitutions. Each advancement increased the key space and complexity, but each was eventually broken, often with devastating consequences during wartime. The lesson from this history is clear. Cryptographic security is not permanent. Algorithms that seem unbreakable today may fall to advances in mathematics or computing power. This is why we constantly evaluate and update our cryptographic standards. Shannon's principles, confusion and diffusion. In 1949, Claude Shannon published a landmark paper titled Communication Theory of Secrecy Systems. This paper, along with his earlier work on information theory, established the mathematical foundations of cryptography. In this paper, he introduced two principles that remain the foundation of modern cipher design: confusion and diffusion. Confusion refers to making the relationship between the ciphertext and the key as complex as possible. If you change one bit of the key, the ciphertext should change in an unpredictable way. A good cipher should make it impossible to determine any information about the key by analyzing the ciphertext, even if you have access to both plaintext and ciphertext pairs. This is typically achieved through substitution operations, where bytes or bits are replaced according to complex rules derived from the key. Let me give you a concrete example of confusion. In AES, the subbytes operation replaces each byte using a substitution table called an S-box. This S-box is carefully designed so that small changes in input produce large changes in output. The relationship between input and output is highly nonlinear, meaning you cannot predict the output from the input using simple mathematical relationships. Diffusion refers to spreading the influence of each plaintext bit over many ciphertext bits. If you change one bit of the plaintext, at least half of the ciphertext bits should change. Similarly, changing one bit of ciphertext should affect many bits of the recovered plaintext. This prevents attackers from analyzing patterns in the plaintext by looking at the ciphertext. Diffusion is typically achieved through permutation and mixing operations. Consider what happens without diffusion. If changing one plaintext bit only changed one ciphertext bit, an attacker could analyze the ciphertext bit by bit, dramatically reducing the search space. With proper diffusion, changing any bit causes a cascade of changes throughout the ciphertext, making such analysis impossible. Modern ciphers achieve both confusion and diffusion through multiple rounds of operations. Each round applies substitution for confusion and permutation for diffusion, and the effects compound with each round. This is why AES uses 10, 12, or 14 rounds depending on key size. Fewer rounds would leave statistical patterns that attackers could exploit. The exact number of rounds is determined through cryptanalysis. Designers analyze how many rounds are needed to achieve full diffusion and how many rounds provide adequate security margin against known attack techniques. They then add extra rounds for safety. This is why reducing the number of rounds in a cipher implementation, even slightly, can catastrophically weaken security. The Avalanche Effect. Closely related to diffusion is the Avalanche Effect. A good cipher should exhibit strong avalanche behavior. Changing a single bit of the input, whether plaintext or key, should change approximately 50% of the output bits, with each output bit having a 50% probability of changing. Let me demonstrate this with a thought experiment. Suppose we encrypt the message "hello" with AES using a specific key, and we get some ciphertext. Now we change one bit in the key. If the cipher has good avalanche properties, the new ciphertext will differ from the original in about 64 of its 128 bits. Furthermore, there will be no pattern to which bits changed. It will appear random. The avalanche effect is essential because it prevents attackers from gaining information through incremental analysis. If changing one key bit only changed a few ciphertext bits, an attacker could potentially search for the key bit by bit, requiring only n times 2 attempts rather than 2 to the power of n attempts. Kerckhoffs Principle. Before we go further, let me emphasize a crucial principle articulated by August Kerckhoffs in 1883. A cryptographic system should be secure even if everything about the system, except the key, is public knowledge. This might seem counterintuitive at first. Should we not keep the algorithm secret too? The answer is no, And here's why. History has shown repeatedly that secret algorithms eventually get reverse-engineered, leaked, or discovered. When that happens, all systems using that algorithm are immediately compromised. Furthermore, secret algorithms cannot be publicly analyzed by cryptographers, so weaknesses may go undetected for years. Consider the example of the CSS encryption used in DVDs. The algorithm was kept secret, but it was eventually reverse-engineered in 1999. The weakness discovered, a 40-bit effective key length and flawed key scheduling, had been present all along but hidden from public scrutiny. If the algorithm had been public, these weaknesses would have been identified and addressed much earlier. Modern cryptographic algorithms like AES and ChaCha20 are completely public. Anyone can download the specifications and implement them. Their security comes entirely from the secrecy of the key, not from obscurity of the algorithm. This approach has been validated by decades of public cryptanalysis. These algorithms have been studied by thousands of researchers and remain secure. This principle has a practical implication for you as security professionals. Never trust proprietary encryption algorithms. If a vendor will not tell you what algorithm they use, assume it is weak. Demand standard algorithms like AES or ChaCha20. Computational security. One more foundational concept before we move on. Modern cryptography is based on computational security rather than information theoretic security. Information theoretic security means the ciphertext contains no information about the plaintext, regardless of computational power. The one-time pad achieves this. If you XOR your message with a truly random key of equal length, the ciphertext is perfectly secure. However, this requires keys as long as messages, which is impractical for most applications. Computational security means the ciphertext may theoretically contain information about the plaintext, but extracting it would require computational resources beyond any practical limit. When we say A.E.S-256 provides 256 bits of security, we mean that the fastest known attack requires approximately 2 to the power of 256 operations. Even if you had a computer performing 1 trillion operations per second, running since the Big Bang, you would not have completed a tiny fraction of this search. This is the basis for all practical symmetric cryptography. We design algorithms where the only viable attack is brute force key search, and we make keys long enough that brute force is infeasible. Part 2. Block ciphers versus stream ciphers. Symmetric ciphers come in two fundamental varieties: block ciphers and stream ciphers. Understanding the difference is essential for choosing the right tool for each situation. Block ciphers. A block cipher operates on fixed-size blocks of data. For example, AES processes data in 128-bit, 16-byte blocks. The cipher takes a block of plaintext and a key and outputs a block of ciphertext of the same size. The operation is deterministic. The same plaintext block and key always produce the same ciphertext block. If your plaintext is exactly 16 bytes, wonderful, you encrypt it directly. But what if your plaintext is longer or shorter? For plaintext longer than one block, we use modes of operation, which we will discuss in detail shortly. Modes of operation define how to handle multiple blocks securely, including how to add randomization so identical plaintext blocks do not produce identical ciphertext blocks. For plaintext shorter than one block, we need padding, adding extra bytes to fill the block. The most common padding scheme is P.K.C.S, #7, where you add bytes equal to the number of padding bytes needed. For example, if you need 5 bytes of padding, you add 5 bytes each containing the value 5. If you need 1 byte of padding, you add 1 byte containing the value 1. If your message is exactly a multiple of the block size, you add a full block of 16 bytes, each containing the value 16. This padding scheme is unambiguous. The receiver can always determine how many padding bytes to remove by looking at the value of the last byte. However, padding has been the source of security vulnerabilities, particularly padding oracle attacks, which we will discuss later. Block ciphers are deterministic by themselves. The same plaintext and key always produce the same ciphertext. This is actually a problem, which is why we always use them with modes of operation that introduce randomness through initialization vectors. We will explore this in detail when we discuss ECB mode and why it is dangerous. The internal structure of block ciphers typically involves multiple rounds of operations. Each round applies some combination of substitution, permutation, and key mixing. Common structures include Feistel networks, used by DES split the block in half, process one half through a round function, XOR with the other half, swap, repeat. Substitution permutation networks, used by AES apply substitution to the entire state, then permutation, then key mixing, repeat. Both structures can achieve strong security with sufficient rounds and well-designed round functions. Stream ciphers. A stream cipher generates a pseudo-random key stream from the key and a nonce number used once. This key stream is then XOR'd with the plaintext to produce ciphertext. Decryption works identically. XOR the ciphertext with the same key stream to recover the plaintext. Mathematically, the ciphertext C equals the plaintext P XOR'd with the key stream generated from the key K and nonce. Decryption works identically. The plaintext P equals the ciphertext C XOR'd with the same key stream. Stream ciphers are conceptually simpler and often faster than block ciphers. They can process data byte by byte or even bit by bit, making them ideal for streaming applications where data arrives continuously and you cannot wait for a complete block before encrypting. The key stream generator must be cryptographically secure. It should be computationally infeasible to predict future key stream from past key stream, recover the key from observed key stream, distinguish the key stream from truly random data. ChaCha20 is the most important modern stream cipher. It generates key stream in 64-byte blocks, XOR'd with the plaintext. The key stream generation is fast and parallelizable. The critical requirement for stream ciphers is that you must never reuse a nonce with the same key. If you do, an attacker can XOR two ciphertexts together to eliminate the key stream, leaving them with the XOR of two plaintexts. C1 XOR'd with C2 equals P1 XOR'd with P2, because the key stream cancels out. The XOR of two plaintexts often reveals significant information about both, especially if they contain natural language or structured data. This two-time pad attack has broken numerous poorly designed systems. Comparing block and stream ciphers. Comparing the two, block ciphers process data in fixed-size blocks and require padding, while stream ciphers process bits or bytes with no padding needed. Random access depends on the mode for block ciphers, but is available with seekable stream ciphers. Parallelization depends on mode for block ciphers, but is usually possible with stream ciphers. Error propagation is mode-dependent for block ciphers, but only affects a single bit in stream ciphers. Hardware support via AES-NI is common for block ciphers, but less common for stream ciphers. The primary modern block cipher is AES, and the primary modern stream cipher is ChaCha20. In practice, the distinction has blurred. CTR mode turns a block cipher into a stream cipher, and many stream ciphers internally use block-like structures. The choice between AES and ChaCha20 is more about hardware support and implementation properties than the block or stream distinction. Part 3. Legacy Algorithms, DES and Triple DES. Data Encryption Standard, DES. Let us start our tour of specific algorithms with DES, the Data Encryption Standard. Understanding DES is important not because you should use it, you absolutely should not, but because it illustrates fundamental concepts and explains why we have the algorithms we use today. DES was developed by IBM in the early 1970s, modified by the NSA, National Security Agency, and adopted as a federal standard in 1977. For over 2 decades, it was the most widely used encryption algorithm in the world. Banks, governments, and businesses worldwide relied on DES to protect sensitive information. DES is a block cipher that operates on 64-bit blocks with a 56-bit key. Wait, you might say, we usually talk about key sizes and powers of 2, so why 56 bits? The answer is that the key is actually stored as 64 bits, but 8 of those bits are parity bits used for error detection, leaving only 56 bits of actual key material. This design decision, influenced by the NSA, was controversial at the time and remains so. Many believe the NSA deliberately weakened the algorithm. The algorithm consists of 16 rounds of a structure called a Feistel network. In each round, the 64-bit block is split into two 32-bit halves, left, L, and right, R. The right half is processed through a function f that involves expansion from 32 to 48 bits, XOR with the round subkey, 48 bits, processing through 8 substitution boxes, S boxes, reducing back to 32 bits. Permutation. The output of f is XORed with the left half. The halves are swapped. Process repeats with the next round subkey. The S boxes are the core of DS's security. They provide the nonlinearity, confusion, that makes the cipher resistant to linear and differential cryptanalysis. The design of these S boxes was kept secret for years, leading to speculation about hidden weaknesses. When differential cryptanalysis was publicly discovered in the 1990s, analysis showed that the DS S boxes were actually optimally resistant to this attack, suggesting the NSA knew about differential cryptanalysis decades before academic researchers. DS was groundbreaking for its time, but it has two fatal flaws for modern use. Key size too small. With only 56 bits, there are 2 to the power of 56, or about 72 quadrillion possible keys. In 1977, this seemed impossibly large. By 1998, the Electronic Frontier Foundation built a machine called Deep Crack that could break DS in under 3 days for about $250,000. Today, you could break DS in hours using cloud computing for a few $100s, or with dedicated hardware in minutes. Block size too small. 64-bit blocks lead to problems when encrypting large amounts of data with the same key. After about 2 to the power of 32 blocks, 32 gigabytes, birthday attacks on certain modes become practical, leading to information leakage. The key size problem was evident even in 1977. Researchers argued for at least 80 bits, preferably more. The 56-bit limit was a political compromise, and history has vindicated the critics. DS should never be used for new systems. It is included here only for historical understanding and because you may encounter it in legacy systems. When you do, your first priority should be migrating to modern algorithms. Triple DS. When DES's weaknesses became apparent, the industry needed a quick fix. Organizations had invested heavily in DES hardware and software, and a complete replacement was not immediately feasible. The solution was Triple DES, also called Triple DES or TDA, Triple Data Encryption Algorithm. The idea is simple: apply DS 3 times with different keys. The most secure variant uses 3 independent keys, K1, K2, K3, and performs. Ciphertext equals: first encrypt the plaintext with key 1, then decrypt the result with key 2, then encrypt again with key 3. Note the middle operation is decryption, not encryption. This encrypt-decrypt-encrypt pattern, ED, was chosen for backward compatibility. If you set K1 equals K2 equals K3, you get standard DS. This allowed triple DS implementations to interoperate with legacy DS systems when needed. With 3 56-bit keys, triple DS has a nominal key strength of 168 bits. However, due to meet-in-the-middle attacks, the actual security is closer to 112 bits with 3 keys. The attack works by encrypting from one side and decrypting from the other, looking for matches in the middle. This reduces the effective security significantly. A 2-key variant, where K1 equals K3, is also common, providing about 80 bits of security. This variant uses only 112 bits of key material and was popular when 168-bit keys seemed excessive. Triple DS solved the key size problem but introduced new issues. Very slow, triple DS requires 3 DS operations per block, making it 3 times slower than DS, which was already not fast by modern standards. On modern hardware, triple DS is 50 to 100 times slower than AES. Still has 64-bit blocks. The birthday attack problem remains. After encrypting about 32 gigabytes with one key, security degrades. The Sweet 32 attack demonstrated this practically in 2016. Awkward key handling. Managing 3 related keys is more complex than managing one key. NSD deprecated triple DES in 2023 and has set 2030 as the date after which it should no longer be used, even in legacy systems. If you are working with systems that still use triple DES, begin migration planning now. The lesson from DES and triple DES is clear. Security requirements evolve, and algorithms that were adequate decades ago may be dangerous today. Always use current standards and plan for future migration. Part 4. The Advanced Encryption Standard, AES. The AES Competition. By the late 1990s, the cryptographic community agreed that a replacement for DES was needed. Rather than developing an algorithm in secret, as was done with DES, NSD organized an open competition. This was a revolutionary approach that has since become the standard for cryptographic standardization. The competition began in 1997 with a call for submissions. Requirements included 128-bit block size, double DES's 64 bits, support for 128, 192, and 256-bit keys, efficient in both hardware and software, royalty-free. 15 algorithms were submitted from teams around the world. These underwent 3 years of intense public analysis. Cryptographers, academics, and practitioners worldwide evaluated security, performance, and implementation characteristics. This open process meant that any weaknesses would likely be discovered before standardization. The 5 finalists were Mars IBM, RC6, RSA Security, Reindahl, Joan Damon and Vincent Ridgman, Serpent, Ross Anderson, Eli Byam, Lars Knudsen, Twofish, Bruce Schneier et al. In 2001, Reindahl, pronounced roughly Reindahl, was selected as the new advanced encryption standard. It won because of its combination of security, performance, and elegance. The algorithm is mathematically clean, runs efficiently on everything from 8-bit microcontrollers to 64-bit servers, and has good resistance to side-channel attacks. Reindahl was designed by 2 Belgian cryptographers, Joan Damon and Vincent Ridgman. It built on their earlier work on the square cipher and introduced the innovative wide trail strategy for ensuring diffusion. AES Structure. AES is a block cipher operating on 128-bit blocks. Unlike Reindahl, which supported variable block sizes, 128, 192, or 256 bits, the AES standard fixed the block size at 128 bits. 3 key sizes are supported. A.E.S, -128, 128-bit key, 10 rounds. A.E.S, -192, 192-bit key, 12 rounds. A.E.S, -256, 256-bit key, 14 rounds. The state is represented as a 4x4 matrix of bytes. For rows, for columns, 16 bytes equals 128 bits. Each round transforms this entire state through 4 operations. Let me walk through each operation in detail. Subbytes, substitution. Each byte of the state is replaced using a substitution table, SBox. This single SBox is applied to all 16 bytes independently. The SBox is a fixed 256-entry lookup table that provides the confusion property. The SBox is not arbitrary. It is derived from the mathematical inverse in Galois field of 2 to the power of 8, followed by an affine transformation. This design ensures high nonlinearity, meaning the output cannot be approximated by simple linear functions of the input. This resistance to linear approximation is crucial for security against linear cryptanalysis. Shift rows, permutation. The rows of the state matrix are shifted by different amounts. Row 0, no shift. Row 1, shift left by 1 byte. Row 2, shift left by 2 bytes. Row 3, shift left by 3 bytes. This simple operation ensures that bytes from each column are spread across different columns after the next operation. It begins the diffusion process by moving data between columns. Mix columns, mixing. Each column is treated as a polynomial and multiplied by a fixed polynomial in Galois field of 2 to the power of 8. More intuitively, each output byte in a column is a specific linear combination of all 4 input bytes in that column. This operation completes the diffusion process. After subbytes, confusion, and shift rows, Mixed columns ensures that each byte affects all 4 bytes in its column. Combined with shift rows, it ensures that after a few rounds, every byte of the input affects every byte of the output. Add round key. Key mixing. The round key is XORed with the state. Each round uses a different 128-bit round key derived from the main key through the key schedule. The key schedule expands the original key, 128, 192, or 256 bits, into 11, 13, or 15 round keys, 10, 12, or 14 rounds plus an initial key. The key schedule uses sub-bytes and round constants to ensure that the round keys are sufficiently different from each other. The round structure is: initial add round key, rounds 1 through n, 1 sub-bytes, shift rows, mixed columns, add round key. Final round n, sub-bytes, shift rows, add round key, no mixed columns. The final round omits mixed columns because it would add computational cost without security benefit. Its effect would be cancelled by the inverse mixed columns in the first decryption round. Security of AES. AES has been intensively studied for over 2 decades. It has withstood extensive cryptanalysis from the world's best cryptographers. No practical attack better than brute force has been found. The best-known attacks include by-click attacks. 2011, these reduced the complexity of attacking A.E.S-128 from 2 to the power of 128 to 2 to the power of 126.1, AE.S-192 from 2 to the power of 192 to 2 to the power of 189.7, and AE.S-256 from 2 to the power of 256 to 2 to the power of 254.4. While these are theoretical improvements, they are still astronomically infeasible. The difference between 2 to the power of 256 and 2 to the power of 254 is about a factor of 4, meaningless when both numbers are impossibly large. Related key attacks. These require the attacker to encrypt with multiple keys that have specific mathematical relationships. They do not apply to normal use cases where keys are independent. Side-channel attacks. These attack implementations rather than the algorithm itself. By measuring timing, power consumption, or electromagnetic emissions, attackers may learn information about the key. AES is somewhat vulnerable to cache timing attacks in software implementations that use lookup tables. Hardware implementations with AES-NI are largely immune. Some important notes about choosing AES key sizes. A.E.S-128 provides 128 bits of security, which is sufficient for most applications today. This level of security is far beyond any foreseeable computational capability. Even with quantum computers, Grover's algorithm only reduces this to 64 bits of security, which remains strong. A.E.S-256 is often chosen for high-security applications and to provide margin against future cryptanalytic advances. It also provides 128 bits of security against quantum computers versus 64 bits for A.E.S-128, making it the recommended choice for long-term security. A.E.S-192 is rarely used. If you need more than 128 bits, you typically go straight to 256. The additional complexity of A.E.S-192 provides little benefit over A.E.S-128 for most threat models. Modes of operation. Here is where many implementations go wrong. AES by itself only encrypts 16-byte blocks. To encrypt larger messages, we need modes of operation. The mode determines how blocks are combined and how randomization is introduced. Let me explain the most important modes in detail. ECB, Electronic Codebook. ECB is the simplest mode. Just encrypt each block independently with the same key. This is almost always wrong. The problem is that identical plaintext blocks produce identical ciphertext blocks. The classic demonstration is encrypting a bitmap image. Even though the individual pixel values are encrypted, the overall pattern of the image remains visible because similar regions, sky, grass, skin, produce similar ciphertext. The famous ECB penguin image shows this dramatically. You can clearly see the shape of a penguin in the encrypted image. This weakness has real security implications. Patterns in data reveal information. Identical messages are detectable. Block-level replay attacks are possible. Never use ECB for real encryption. It exists in cryptographic libraries because it is a building block for other modes and has niche uses, like encrypting exactly one block, but it should never be used for general encryption. CBC, Cipher block chaining. CBC addresses ECB's weakness by chaining blocks together. Before encrypting each block, it is XOR'd with the previous ciphertext block. The first block is XOR'd with a random initialization vector 4. Encryption. The initial ciphertext block C0 is the 4. Each subsequent ciphertext block C I equals the encryption of the plaintext block P I XOR'd with the previous ciphertext block C I-1. Decryption. The plaintext block P I equals the decryption of ciphertext block C I XOR'd with the previous ciphertext block C I-1. This ensures that identical plaintext blocks encrypt to different ciphertext blocks because they are XOR'd with different previous ciphertext. The 4 must be unpredictable for each message, typically random, though some protocols use counters. CBC provides good security but has some drawbacks. Sequential encryption. Each block depends on the previous, so encryption cannot be parallelized. Decryption can be parallelized because you only need the current and previous ciphertext blocks. Error propagation. A corrupted ciphertext block affects 2 plaintext blocks, the corrupted block and the next one. Padding oracle attacks. If an attacker can determine whether received ciphertext has valid padding, they can often decrypt the entire message. This was demonstrated devastatingly in the Poodle attack against SSL 3.0 and the Lucky 13 attack against TLS. The 4 must be random and unpredictable. Using a predictable 4, like a counter, can enable chosen plaintext attacks where attackers can verify guesses about plaintext. CTR counter mode. CTR mode turns a block cipher into a stream cipher. Instead of encrypting the plaintext directly, we encrypt a counter value, starting from a nonce, and XOR the result with the plaintext. Keystream generation. Each keystream block I equals the encryption of the nonce concatenated with the counter value I. Encryption and decryption. The ciphertext block I equals the plaintext block I XOR'd with the corresponding keystream block. The counter typically starts at 0 and increments for each block, combined with a unique nonce for each message. This ensures the keystream is unique. CTR mode has significant advantages. Full parallelization. Both encryption and decryption can be fully parallelized because each block is processed independently once you have the keystream. This enables much higher throughput on multi-core systems. Random access. You can decrypt any block independently by computing its counter value. This is useful for disk encryption where you might read block 1000 without reading blocks 1 to 999. No padding needed. You just generate as much keystream as you need and XOR. If your message is 100 bytes, you generate 112 bytes of keystream, 7 blocks, and use 100 bytes. Single-bit error propagation. A corrupted ciphertext bit only affects one plaintext bit. There is no error spreading. The critical requirement is never reusing a nonce with the same key. If you encrypt 2 messages with the same nonce, C1 equals P1 XOR'd with the keystream. C2 equals P2 XOR'd with the same keystream. Therefore, C1 XOR'd with C2 equals P1 XOR'd with P2 because the keystream cancels out. An attacker can XOR the ciphertext to get the XOR of plaintexts, which often reveals significant information. GCM, Galois counter mode. GCM combines CTR mode encryption with authentication. It provides both confidentiality and integrity, meaning an attacker cannot modify the ciphertext without detection. This is what we call authenticated encryption with associated data, AAD. You can include additional data, like headers, that are authenticated but not encrypted. GCM uses CTR mode for encryption and a polynomial hash called gash for authentication. The output is ciphertext plus an authentication tag, typically 128 bits. GCM is the most widely used authenticated encryption mode. It is used in TLS 1.3 mandatory cipher suite, TLS 1.2, Preferred Cipher Suite. SSH, IPsec. Numerous application protocols. GCM requirements and considerations. Nonce uniqueness. Nonces must never repeat with the same key. A single nonce reuse can catastrophically break authentication. An attacker can forge authentication tags and may recover the authentication key. This is worse than CTR mode nonce reuse because authentication is completely compromised. Nonce size. GCM standard uses 96-bit nonces. With random nonces, birthday collisions become likely after about 2 to the power of 48 messages. For high-volume applications, use deterministic nonces, counters, or algorithms with larger nonces. Tag size. 128-bit tags are recommended. Shorter tags, 96, 64, 32 bits, are allowed but reduce security proportionally. With a 64-bit tag, an attacker has a 1 in 2 to the power of 64 chance of randomly forging a valid tag. Message size limits. GCM is designed for messages up to 2 to the power of 36 blocks, about 64 gigabytes. Longer messages should be split into separately authenticated chunks. Performance. GCM is very fast with hardware acceleration, CLMUL instructions. Without hardware support, the Gash polynomial multiplication is relatively slow. CCM, counter with C.B.C, M.A.C. CCM is another authenticated encryption mode that combines CTR mode encryption with C.B.C, M.A.C authentication. It was designed for constrained environments like IoT devices and is used in Bluetooth Low Energy, Zigbee, IEEE 802.15.4 wireless sensor networks, WPA2 Wi-Fi. CCM has different trade-offs than GCM. No special hardware needed. C.B.C, M.A.C uses the same AES operations as encryption, while GCM's Gash requires different hardware, CLMUL, for optimal performance. Message length required upfront. Unlike GCM, which can process data streaming, CCM needs to know the total message length before starting encryption. This is because the C.B.C, M.A.C is computed before encryption. Generally slower than GCM. On hardware with AES-NI and CLMUL, GCM is faster. On constrained devices without specialized hardware, they may be comparable. Two-pass processing. CCM requires 2 passes over the data, one for MAC, one for encryption. GCM processes data in a single pass. Mode selection summary. Here is a summary of the modes. ECB provides no authentication, is parallelizable, requires padding, and should never be used. CBC provides no authentication, can only parallelize decryption, requires padding, and is used for legacy and specific applications. CTR provides no authentication, is fully parallelizable, needs no padding, and is used as a building block. GCM provides authentication, is parallelizable, needs no padding, and is the general-purpose AED choice. CCM provides authentication, is not parallelizable, needs no padding, and is used for constrained devices. Recommendation. For new applications, always use authenticated encryption. GCM is the default choice when hardware acceleration is available. ChaCha20 Poly 1305, discussed next, is excellent when it is not. Part 5. ChaCha20 and ChaCha20 Poly 1305. The origins of ChaCha20. While AES dominates in hardware, it can be slow on devices without AES-NI instructions. The SBox lookups in software implementations are also vulnerable to cache timing attacks, requiring careful constant-time implementations that further reduce performance. Daniel Bernstein, a prolific cryptographer known for practical and elegant designs, designed the ChaCha20 stream cipher in 2005 for the eStream project. In 2008, he published ChaCha20, an improved variant with better diffusion while maintaining ChaCha20's efficiency. ChaCha20 is a stream cipher that generates a 512-bit keystream block from a 256-bit key, a 96-bit nonce, a 32-bit block counter. It uses only add, rotate, and XOR operations, ARX, which Execute in constant time on virtually all processors. No table lookups. Are simple to implement correctly. Achieve strong diffusion with fewer rounds than SBox-based ciphers. This makes ChaCha20 resistant to timing side-channel attacks inherently, even without special care in implementation. ChaCha20 Structure. The algorithm maintains a 4x4 matrix of 32-bit words. 512 bits equals 64 bytes total. The first row contains 4 constant words, which spell out expand 32-byte K in ASCII, a nothing-up my sleeve constant. The second and third rows contain 8 keywords, totaling 256 bits. The fourth row contains 1 counter word of 32 bits, followed by 3 nonce words of 96 bits total. The quarter-round function operates on 4 words, called A, B, C, and D. It performs 4 steps. First, add B to A, XOR D with A, and rotate D left by 16 bits. Second, add D to C, XOR B with C, and rotate B left by 12 bits. Third, add B to her again, XOR D with A, and rotate D left by 8 bits. Fourth, add D to C again, XOR B with C, and rotate B left by 7 bits. Each round applies this quarter round to first, columns, column rounds. Then, diagonals, diagonal rounds. After 20 rounds, 10 double rounds, the original state is added to the mixed state. This addition provides a crucial nonlinearity and ensures that the key stream cannot be inverted. The resulting 512-bit block is the key stream for that counter value. Increment the counter for the next block. ChaCha20 Poly 1305. Just as GCM combines A.E.S, C.T.R with GASH authentication, ChaCha20 Poly 1305 combines ChaCha20 encryption with Poly 1305 authentication. This combination was standardized in RFC 7539, now RFC 8439, and is now widely deployed. Poly 1305 is a one-time authenticator designed by Bernstein. It takes a 256-bit key and a message and produces a 128-bit tag. The key is single-use. A new key is derived for each message from the ChaCha20 keystream. How ChaCha20 Poly 1305 works. Generate the first keystream block, counter equals 0. Use the first 256 bits as the Poly 1305 key. Encrypt the plaintext using ChaCha20, counter starting at 1. Compute Poly 1305 over the associated data and ciphertext. Output ciphertext and 128-bit tag. Poly 1305 is extremely fast. It processes data in large chunks with only multiplication and addition modulo a prime. The one-time key requirement is satisfied by deriving a new key for each message. ChaCha20 Poly 1305 advantages. Fast without hardware acceleration. Often 3-5x faster than A.E.S, G.C.M in pure software on mobile devices. Constant time by design. No table lookups means no cache timing attacks. Simple implementation, harder to implement incorrectly. Standardized. RFC 8439, TLS 1.3 mandatory cipher suite, widely supported. ChaCha20 Poly 1305 is used in TLS 1.3 mandatory implementation. WireGuard VPN, Signal Protocol, Google Chrome, and Android. Many mobile applications. ChaCha20. Standard ChaCha20 uses a 96-bit nonce. While this is adequate for most uses, it requires careful nonce management. Random nonces have a collision risk after 2 to the power of 48 messages due to the birthday bound. ChaCha20 extends the nonce to 192 bits, making random nonce generation safe for virtually unlimited messages. It works by use the first 128 bits of the nonce with HKDF, a ChaCha20 variant that outputs the core state, to derive a 256-bit subkey. Use the remaining 64 bits as the nonce for standard ChaCha20 with the subkey. This construction is provably secure if ChaCha20 is secure. ChaCha20 Poly 1305 is recommended for distributed systems where coordinating nonces is difficult. High-volume encryption, where 2 to the power of 48 message limit is too low. Applications using random nonces. File encryption, where unique nonces per file are challenging. Libsodium implements ChaCha20 Poly 1305 as its recommended AAD construction. A.E.S, G.C.M versus ChaCha20 Poly 1305. Both are excellent authenticated encryption algorithms. The choice depends on your environment. Prefer A.E.S, G.C.M when hardware acceleration, ASNI, CLMUL, is available. Maximum throughput is critical. Compliance requires NASD algorithms. Interoperability with legacy systems is needed. Prefer ChaCha20 Poly 1305 when running on devices without ASNI, mobile, embedded, older systems. Side-channel resistance is critical. Implementation simplicity is valued. Using random nonces, ChaCha20. In practice, many systems support both and negotiate the best option. TLS 1.3 requires both to be implemented. Part 6. Ascon, Lightweight Cryptography. The need for lightweight cryptography. The Internet of Things has created demand for cryptography that works on extremely constrained devices. Sensors with kilobytes of RAM. Microcontrollers running on coin batteries. RFID tags with minimal circuitry. Industrial control systems with real-time requirements. Standard algorithms like AES, while efficient on modern processors, can be challenging for these devices. AES requires significant code size and RAM for lookup tables. Constant-time AES implementations are even larger. GCM's Gash multiplication is expensive without hardware. In 2019, NSD launched the Lightweight Cryptography Competition to standardize algorithms optimized for constrained environments. After years of evaluation involving 57 initial submissions, NSD announced Ascon as the winner in February 2023. Ascon Design. Ascon was designed by Christoph Dobronik, Maria Eichelceder, Florian Mindel, and Martin Schlaffer from Graz University of Technology and Infineon Technologies. The design prioritizes small state size, 320 bits, simple operations, XOR, and rotation, flexibility across 8-bit, 32-bit, and 64-bit platforms, resistance to side-channel attacks. Ascon uses a sponge construction similar to S.H.A-3, but optimized for small implementations. The core is a 320-bit permutation operating on 564-bit words. The permutation uses a simple round function with addition of round constants, prevents symmetry. Substitution layer, 5-bit SBox applied to 64 parallel slices. Linear diffusion layer, bitwise rotation and XOR. Despite the design targeting 64-bit words, the operations can be efficiently bit-sliced for 8-bit and 32-bit platforms. This means the same algorithm works well across vastly different hardware. Ascon Variants. Ascon provides a family of algorithms. Authenticated encryption. Ascon 128, 128-bit key, 128-bit knots, 128-bit tag, standard security. Ascon 128A, same security but faster, fewer rounds, higher throughput. Hash functions. Ascon hash, 256-bit hash function. Ascon Hasha, faster variant with fewer rounds. Ascon XOF, extendable output function, arbitrary output length. MEC. Ascon MAC, message authentication code. Ascon PRF, pseudo-random function. The availability of EAD, hashing, and MAC from one algorithm family simplifies implementation and reduces code size, important on constrained devices. Ascon Performance. Ascon achieves impressive performance on constrained devices. On 8-bit AVR microcontrollers. Encryption, approximately 15 cycles per byte. Hashing, approximately 20 cycles per byte. On 32-bit ARM Cortex-M. Encryption, approximately 10 cycles per byte. Competitive with AES even without AES hardware. On 64-bit platforms. Very fast, though A.E.S, G.C.M, with hardware is faster. The small state, 320 bits equals 40 bytes. means Ascon requires minimal RAM, important for devices with kilobytes of memory. When to use Ascon? Ascon is designed for constrained environments, not to replace A.E.S, G.C.M on servers. Use Ascon when working with IoT devices, embedded systems, or smart cards. Hardware resources, gates, memory, code size are severely limited. Side-channel resistance is important, and hardware countermeasures are unavailable. You need a single algorithm family for encryption, hashing, and MAC. Power consumption is critical, battery-operated devices. For standard servers, desktops, and mobile devices with modern hardware, A.E.S, G.C.M, and ChaCha20 Poly 1305 remain the recommended choices due to hardware acceleration and mature implementations. Ascon is standardized in NASD Special Publication 800-232, expected 2024, and will be mandated for U.S. government IoT applications. Part 7. Key Management. The key management problem. We have discussed many excellent encryption algorithms, but I must emphasize something crucial. Most cryptographic failures are not due to broken algorithms. They are due to broken key management. You can use A.E.S-256, G.C.M, the gold standard, and still have completely insecure encryption if the key is derived from a weak password. The key is stored in plain text in a configuration file. The same key is used for years without rotation. Keys are transmitted insecurely. Key generation uses a weak random number generator. A study of cryptographic vulnerabilities found that key management issues account for far more real-world breaches than algorithmic weaknesses. The algorithm is usually the strongest link. Everything else around it is weaker. Let me discuss the tools and practices for proper key management. Key generation. Keys must be generated using cryptographically secure random number generators, CSBRNGs. On modern operating systems, Linux and Mac OS, the dev-urandom device, or the get-random system call. Windows, crypt-gen-random or bcrypt-gen-random. Never use. Standard library random functions, rand, random. Current time as a seed. Predictable sources like process IDs. Insufficient entropy sources. Key generation code should be simple. Call the OS CSBRNG and request the required number of bytes. Libraries like libsodium provide random bytes, functions that do this correctly. For A.E.S-256, you need 32 cryptographically random bytes. That is it. Do not complicate this. Key derivation, HKDF. HMAC-based key derivation function, HKDF, standardized in RFC 5869, is used to derive cryptographic keys from other key material. It is particularly useful for deriving multiple keys from a shared secret, like after Diffie-Hellman, expanding short keys into longer ones, adding context to key derivation. HKDF works in two stages. Extract takes the input key material and an optional salt, producing a pseudo-random key called PRK. This concentrates the entropy from possibly non-uniform input. The PRK equals HMAC applied to the salt and the input key material. Expand takes the PRK and optional context info, producing output key material of any desired length. Each output block is computed by applying HMAC to the PRK with the previous block, the info string, and a counter byte. The salt should be random if possible, but even a non-secret constant salt improves security compared to no salt. The info parameter allows deriving different keys for different purposes from the same input. This is called domain separation. Example use case. After Diffie-Hellman key exchange produces a shared secret, use HKDF to derive separate keys for encryption and authentication. The encryption key equals HKDF applied to the shared secret, a salt, and the string encryption. The authentication key equals HKDF applied to the same shared secret and salt, but with the string authentication. Password-based key derivation PBKDF2. Passwords are not suitable directly as cryptographic keys. They lack entropy, typically 20 to 40 bits versus 128 to 256 bits needed. They are vulnerable to dictionary attacks. Common passwords appear frequently. Password-based key derivation function 2, PBKDF2, standardized in RFC 8018, transforms passwords into keys while intentionally being slow to compute. PBKDF2 applies a pseudo-random function, typically HMA.C, SHA256, to the password many times, tens or hundreds of thousands of iterations. This iteration count, cost factor, makes brute force attacks expensive. The derived key DK equals PBKDF2 applied to the password, SALT, number of iterations, and desired output length. The SALT, at least 128 bits, random per password, prevents rainbow table attacks and ensures identical passwords produce different keys. However, PBKDF2 has limitations. It does not require much memory, so GPUs can attack it efficiently. It can be parallelized easily. Each HMAC iteration is relatively cheap on specialized hardware. For password hashing specifically, modern algorithms like Argon 2ID are superior because they require significant memory and resist GPU or ASIC acceleration. We will cover password hashing in detail in Lecture 11. PBKDF2 remains appropriate when interoperability with older systems is needed. The protocol specification requires it, like WPA2. Memory hard functions are unavailable. When using PBKDF2, use at least 310,000 iterations for HMA.C, SHA256, OWASP 2023 recommendation. Key storage. Production systems should never store cryptographic keys in plain text. Options include hardware security modules, HSMs, dedicated hardware devices that store keys and perform cryptographic operations. Keys never leave the HSM in plain form. Tamper-resistant physical design, used by financial institutions, certificate authorities, cloud providers. Examples: Thales Luna, AWS Cloud HSM. Key Management Services, KMS, cloud services that provide HSM-backed key storage. AWS KMS, Azure Key Vault, GCP Cloud KMS. Audit logging, access control, automatic rotation. Keys managed through APIs. Cost-effective alternative to dedicated HSMs. Secure enclaves. CPU features that create isolated execution environments. Intel SGX, software guard extensions. ARM Trust Zone. Keys protected from even privileged system software. Subject to side-channel attacks, foreshadow, etc. Operating system key stores. Windows POPI, Data Protection API. macOS Keychain. Linux kernel keyring. Keys encrypted with user or system credentials. Appropriate for desktop applications. Encrypted configuration. Keys encrypted with a master key. Master key protected by one of the above methods. Common for development and lower security applications. Never store keys in source code. Store keys in plain text configuration files. Store keys in environment variables, leak in logs, error messages. Commit keys to version control. Use secrets management instead. Key rotation. Keys should be rotated periodically. Why? Limiting exposure. If a key is compromised, rotation limits how much data is affected. Data encrypted before the compromise and after key rotation remains protected. Cryptographic hygiene. Some modes have limits on how much data should be encrypted with one key. GCM, approximately 2 to the power of 32 blocks, 64 gigabytes, per nonce, 2 to the power of 32 nonces per key. After these limits, security guarantees weaken. Compliance requirements. Many standards require periodic key rotation. PCI DSS requires annual key rotation for encryption keys. Some regulations specify maximum key lifetimes. Algorithm transitions. Regular rotation makes it easier to transition to new algorithms or larger key sizes. A good key management system supports versioning. Encrypt new data with the latest key version. Decrypt data with whatever key version was used to encrypt it. Gradually re-encrypt old data with new keys. Eventually retire old key versions. This allows smooth transitions without disruption. Key hierarchies. Large systems often use key hierarchies. Master keys, key encryption keys, stored in HSMs or KMS, used to encrypt other keys. rotated infrequently with careful planning. Data encryption keys, DKs. Encrypt actual data. Encrypted by master keys when stored. Rotated frequently. May be unique per record or per session. Session keys. Used for single communication sessions. Derived from key exchange, Diffie-Hellman. Discarded after session ends. This hierarchy provides defense in depth and flexibility. If a DK is compromised, only data encrypted with that key is affected, not the entire system. Part 8. Best Practices and Recommendations. Let me conclude with concrete recommendations for using symmetric cryptography in 2025 to 2026. Algorithm selection. For general-purpose authenticated encryption, A.E.S-256, G.C.M, or ChaCha20 Poly 1305. Both are excellent choices. Prefer A.E.S, G.C.M when hardware acceleration, AES-NI, is available. Prefer ChaCha20 Poly 1305 on mobile devices without AES-NI or when constant time implementation is critical. Both are mandatory in TLS 1.3. If you support TLS, you already have both. For constrained IoT devices, Ascon 128 or Ascon 128A. NGSD standardized for this purpose. Efficient even on 8-bit microcontrollers. Single algorithm family for encryption and hashing. For encrypting many messages with random nonces, ChaCha20 Poly 1305. 192-bit nonce eliminates birthday concerns. Safe for virtually unlimited messages. Available in libsodium. Never use. DS, 56-bit key, trivially broken. Triple DES, slow, deprecated, end of life, 2030. RC4, multiple practical attacks. ECB mode, patterns visible. Custom or proprietary algorithms. Implementation guidance. Use established libraries. Do not implement cryptographic algorithms yourself. Use libsodium, excellent API design, misuse resistant. OpenSSL, comprehensive, widely deployed. Boring SSL, Google's OpenSSL fork, cleaner code. Platform libraries, .NET, Java cryptography architecture. Go crypto and X packages. Even experts make implementation mistakes. Constant time implementation, side channel resistance, and correct padding are subtle. Trust audited code. Always use authenticated encryption. Raw encryption, without authentication, allows attackers to modify ciphertext without detection. This has enabled devastating attacks. Padding oracle attacks. Bit flipping attacks. Format confusion attacks. Always use GCM, CCM, or ChaCha20 Poly 1305. Never use CBC, CTR, or other non-authenticated modes for encryption without adding separate authentication. Never reuse nonces. This is the most common implementation error. GCM nonce reuse completely breaks authentication. Use counters for sequential systems. Ensure persistence across restarts. Use random nonces with ChaCha20 for distributed systems. Track nonces if necessary to detect reuse. Derive keys properly. Use HKDF for key derivation from high-entropy sources. Use Argon 2 ID for passwords, covered in Lecture 11. Add domain separation, different info strings for different purposes. Plan for algorithm agility. Design systems so algorithms can be changed without major modifications. Include algorithm identifiers in encrypted data formats. Use abstraction layers in code. Do not hardcode algorithm choices throughout the codebase. Common implementation mistakes. Let me highlight mistakes I have seen in real systems. Using ECB mode, usually because it is the default in some libraries or because developers do not understand modes. Nonce reuse. Using a constant nonce, reusing nonces after restart, no persistent counter, or insufficient random nonce length. Hard-coded keys. Keys in source code, committed to repositories, discoverable through reverse engineering. Weak key derivation, using MD5 or S.H.A-256 hash of password without iterations. Using timestamp as key. Insufficient salt. No authentication, using A.E.S, C.B.C, or A.E.S, C.T.R without HMAC, allowing ciphertext modification. Short tags, using 32-bit or 64-bit authentication tags to save space, dramatically reducing forgery resistance. Ignoring tag verification, checking tag after decryption instead of before, or not checking at all. Random number generation, using predictable sources, reseeding poorly, insufficient entropy collection. Looking forward, post-quantum considerations. Symmetric cryptography is well-positioned for the post-quantum era. Grover's algorithm, running on a sufficiently powerful quantum computer, can search 2 to the power of n possibilities in 2 to the power of n over 2 operations. This effectively halves the security of symmetric algorithms. The response is simple. Use 256-bit keys. 8.E.S-256 provides 128 bits of post-quantum security, which is more than sufficient. ChaCha20 with its 256-bit keys is similarly secure. Symmetric cryptography does not need fundamental changes for the quantum era. This is why A.E.S-256 and ChaCha20, both 256-bit key algorithms, are the recommended choices. They are already quantum-resistant with comfortable security margins. Asymmetric cryptography faces a much bigger challenge, as we will discuss next week. But your symmetric encryption choices today will remain secure against quantum computers. Conclusion. Today we covered the fundamentals of symmetric cryptography, from Shannon's principles of confusion and diffusion through modern algorithms like AES, ChaCha20, and Ascon. The key takeaways are: use authenticated encryption, 8.E.S-G.C.M, or ChaCha20 Poly 1305, with unique nonces. Raw encryption without authentication is dangerous. A.E.S-256 provides excellent security, including against future quantum computers. It is the gold standard for a reason. ChaCha20 Poly 1305 is an excellent alternative, especially when hardware acceleration is unavailable or when constant time implementation is critical. Ascon is the new standard for constrained devices, providing efficient authenticated encryption on IoT and embedded systems. DS and triple DS are obsolete. Never use them in new systems and plan migration from legacy systems. Proper key derivation and management are essential. Good algorithms with bad key management provides no security. Never implement cryptographic algorithms yourself. Use established, audited libraries. Plan for algorithm agility. Cryptographic standards evolve. Your systems should be able to evolve with them. Next week, we will explore asymmetric cryptography, which solves the key distribution problem that is symmetric cryptography's fundamental challenge. How do two parties who have never met share a secret key? The answer revolutionized cryptography and enabled the secure internet we rely on today. Discussion questions. Why do most real-world cryptographic failures stem from key management rather than algorithm weaknesses? How should organizations plan their cryptographic strategy to maintain algorithm agility as standards evolve? What role will lightweight cryptography like Ascon play as the Internet of Things expands? Thank you for your attention. See you next week. Review questions. Explain Shannon's principles of confusion and diffusion. How are they implemented in modern ciphers? Why was DS retired? And what were the main weaknesses that led to its replacement? Describe the AES selection process and explain why Randall was chosen. Compare ECB and CBC modes of operation. Why should ECB never be used for encrypting data? What is authenticated encryption, and why is it preferred over encryption without authentication? Compare A.E.S-G.C.M and ChaCha20 Poly 1305. In what situations would you prefer each? What is the purpose of HKDF, and how does it differ from PBKDF2? Explain why nonce reuse in GCM mode is catastrophic for security. Key terms. AAD, authenticated encryption with associated data, providing both confidentiality and integrity in a single operation. AES, advanced encryption standard, a symmetric block cipher using 128-bit blocks and 128, 192, or 256-bit keys. Ascon, NIST standardized lightweight authenticated encryption algorithm for constrained devices. Authenticated encryption, encryption that provides both confidentiality and integrity verification. Block cipher, a cipher that encrypts fixed-size blocks of plaintext. CBC, cipher blockchaining, a block cipher mode that XORs each plaintext block with the previous ciphertext block. CCM, counter with C.B.C, M.A.C, an authenticated encryption mode combining CTR encryption with C.B.C, M.A.C authentication. ChaCha20, a stream cipher designed by Daniel Bernstein, used with Poly 1305 for authenticated encryption. Confusion, Shannon's principle of making the relationship between key and ciphertext complex. CTR, counter mode, which turns a block cipher into a stream cipher. DS, data encryption standard, a retired 56-bit key block cipher. Diffusion, Shannon's principle of spreading plaintext influence across the ciphertext. ECB, electronic codebook, a block cipher mode that encrypts each block independently. GCM, Galois counter mode, an authenticated encryption mode combining CTR with GASH. HKDF, HMAC-based key derivation function for deriving keys from other key material. Key rotation, the practice of periodically replacing cryptographic keys. Knots, a number used once, required by many encryption modes to ensure unique ciphertexts. PBKDF2, password-based key derivation function 2, for deriving keys from passwords. Stream cipher, a cipher that encrypts plaintext 1 bit or byte at a time. Symmetric encryption, encryption where the same key is used for both encryption and decryption. Triple DS, a legacy symmetric cipher applying DS 3 times with 2 or 3 different keys. ChaCha20, an extended nonce variant of ChaCha20, supporting 192-bit nonces for large-scale encryption. References and further reading. NGST FIPS 197, Advanced Encryption Standard, AES. RFC 5116, an interface and algorithms for authenticated encryption. RFC 8439, ChaCha20 and Poly 1305 for IETF protocols. RFC 5869, HMAC-based extract and expand key derivation function, HKDF. NSDSP 800-38D, recommendation for block cipher modes of operation, Galois counter mode, GCM. NSD lightweight cryptography standardization, Ascon selection, 2023. Bernstein, DJ, the Salsa 20 family of stream ciphers. Damon, J. Ridgman, V. The design of Reindahl. AES, the advanced encryption standard. Shannon, C. Communication theory of secrecy systems, 1949. Kerckhoffs, A. La cryptographie militaire, 1883. NSD SP 800-57, recommendation for key management. OWASP password storage cheat sheet.